All right. So let's talk about stuff for today. Share my screen. No. Yes. Yes. Alrighty. So last week we talked about. Oops. I don't know who you are. Go away. Gotta love spam callers. If you're calling from a 407 area code, which is where I used to be, got when I lived down in Florida, and your name doesn't pop up, there's a very, very strong chance that I do not know who you are. You're just spoofing a phone number to try to get me to take it. All right, so last week we talked about graph problems and we talked about solving the traveling salesperson problem and finding best routes. Today is going to be a little bit of a different type of problem. We're going to talk about the Tower of Hanoi. But before we do, I just want to go through a couple of house cleaning things. Excuse me. So I know some of you guys are still having some issues with the last project. So try to, if you've got questions and stuff, email me. You come to my virtual office hours. Email me and say you can't come to the virtual office hours, but see if we can do something different. I'll work with you. We do want to try to get those in. Out of curiosity, would anyone like to volunteer maybe why that seems to be a little bit harder than I was expecting it to be? Is it just kind of a unique type of problem, or is it something that's just something you got to think differently about, or is it really complicated? I just didn't see it as being
No,
really
I
complicated.
see the problem. So when I wrote the code at first, so I got it to work because once I figured out the whole dictionary thing, it took me like 30 minutes to get both sides to work, like going from numbers to letters and from letters
Mm-hmm.
back to numbers. And then it still took me like another 5 minutes to get it to pull from a text file.
Mm.
But I mean, as you know, like my only problem is still because it'll still convert from the letters to numbers, but it won't go from numbers to letters.
Oh,
Because and also yeah, but I mean also there's something really really annoying. And I tested it out, and it actually has nothing to do with the fact that I'm using a string array.
right. I didn't think it would.
Because I've tested my string array in a separate program.
Mm-hmm.
But even now, like say when I come down to my state where I have like my tri parse here, and I have like my out convert in like above the part where it's supposed to go into the converter two. I also put I guess a write line, like a console write line convert, like trying to see like because I have the int 32 tri parse lines, so it pulls from the line.
Mm-hmm.
And it said out convert, the console write line convert, and it doesn't write anything. Just nothing comes out.
Hmm. Um, I'm going to ask a silly question, and because I've done this before, don't think that this is actually coming from experience. Not, I'm trying to say anything about you, but are you making sure you're returning something
In the
in
in
your
the
convert function?
oh no, yeah, no, my converter two function does return. It does return. So well, okay, so my converter two function itself is void, and at the very end of it, it writes.
Okay, so it's supposed to write something. So
Yeah,
you don't return something, you write something. Okay.
yes, it writes something. What I'm saying is, I did it before. Like, I'm calling this before I even get into the converter. Like, so
Oh, okay.
I'm still in my main program where I'm
Oh,
asking
okay.
it to console write line the I guess the value I'm going to put into the integer
Ah,
converter, and
okay.
it keeps giving me a zero.
Okay. Um, if you want to take a look at that later, we can take a look at that later.
Yeah.
And see what's going on. So, anyone else want to chime in? I think everyone's had a little bit of issue with this. Um,
Well, I've had
Is
the one.
mine still okay? Did you want me to use dictionary? I still haven't messed with it since I turned it in that day.
You are not required to use dictionary. Um,
I know
I
the only thing you can't really do is actually run it just because it's pulling a file from my my database. You don't actually have it, so but you
Same,
saw it
same.
working
I
before.
yeah, well, and I can go in and I can change where the file points. So
Yeah.
Yeah, that would be the only thing. Mine is working too. After the hint you gave me, I just fixed everything and it's good
okay,
to go.
you're able to
Okay,
get it.
I'm with it.
Okay, so
So I'm the only one with the problem.
well, left. I think everyone had some sort of problem at some point in converting numbers to Roman numerals, or I think everyone was able to get Roman numerals to numbers okay, but converting numbers to Roman numerals, I think, was the challenge. Is Am I correct on that?
Yes.
Yeah.
I've only had one problem this whole time, and it's this damned. Why won't it?
Why won't I get a value?
Yeah, why
Um,
won't it work?
and so and that's a valid question point, but I think there's some really interesting problems in the conversion process, which is what we're talking about way back when it started was with the ETL is doing that transform process and how we have to convert data sometimes. So anyway, like I said, I was just kind of trying to get a idea if there's something I need to like hints I need to provide or something like that to help people when they when we do this again next term or 2 terms from now or whenever it's going to be. So, all right, let's talk about the Tower of Hanoi. Has anyone ever heard of that term before? Just out of curiosity.
A couple years back, I was playing a Call of Duty campaign, and we went to Hanoi. I fought through the Tower of Hanoi.
All right,
With a,
not the same one.
damn.
So the Tower of Hanoi, there's actually a couple different names for it. If you go digging online, you can do some research. Tower of Brahma, I think is how you pronounce that. There's another one. There's also a Tower of, I think that it's either Shanghai or something like that. Anyway, it's supposedly based off of a children's puzzle. And basically, you have 3 pegs. So you got peg 1 or A, B, and C, if you want to call them that. And then you have a series of discs, and the discs are of different sizes. So you've got disc, different sizes. And the idea is, I want to move all of my disc that are from biggest on the bottom to smallest. I can't have a disc that's bigger than the one below it on top. Okay, my disc have to be larger ones on the bottom, so they have to be stacked like that. And I want to move it from one peg to another peg. It doesn't. I don't have to necessarily go from A to C. I could go from A to B, or I could go from B to C. But I need to move my disc. But I can only move one disc at a time. So if I have one disc, it's real easy. I just move it over. I'm done. If I have 2 discs, then I call them disc 1 is the smaller one, and disc 2 is the bigger one. I can move disc 1 to peg B, then disc 2 can go to peg C, and then disc 1 can go on top of disc 2 on peg C. And now my whole stack is moved. Okay.
Mm-hmm.
So conceptually, that's a real simple thing, right?
Yeah.
Okay. The problem is, as I start adding more and more disk, and I've kind of got it listed here. If I have 2 disks, here's the disk. If I have 3 disks, notice I go from 3 to I now have 7. Okay, I have 7 steps. Those are my 7 steps. A to C, A to B, C to B, A to C. Okay, it just goes back and forth, back and forth.
Yeah.
This starts getting more and more complex over time. Now, what winds up being interesting is there is a recursive algorithm that lets us determine this, and we can work it out. So this is actually a visual representation right here. It's a little animated GIF I found, moving like 5 disks. You can see how long it takes to move the pieces one at a time, back and forth. But it lets you see how the whole thing winds up getting moved, and working in that process. We're still working on that solution, and it's not quite done yet. But I think it's really an interesting problem because you're getting a chance to visually see how do you wind up moving all these different disks for that many of them. And like I said, there's like what, 6 there, 7 there. Okay.
Yeah.
So if you start counting this out and you work out the problem, this is a very inefficient problem. If you have 2 disks, you have 3 moves. If you have 3 disks, you have 7 moves. At a 4th disk, it's 15 moves. Winds up, the big O for this is 2 to the nth power minus 1.
Not fun.
So if you have 1 to the first power is 2, minus 1 is 1. That's your 1 move. If you have 2 to the second power is 4, minus 1 is 3. Okay, that works out. 3, 2 to the third power is 8, minus 1 is 7. You can work this out. Now, here's where the scary part is. There is supposedly, and I don't know how much of this is like an old wives' tale or, what's going on. Supposedly, there are monks that are sitting in this monastery out in the Far East, and they're playing this game. And when this game ends, when they're able to finally move all the pegs from one to the other, the world is supposed to end. And so this is like, was it 2012 with the Mayan calendar? This is like the year 2000 Y2K problem. I've gone through so many end of the world experiences. I'm like, you know what, bring it. I'm ready for next one. So supposedly this is going to happen. But here's the thing: their plan was 64 disc. So if you think, okay, 64 disc, how big a problem is that? Well, here's all your moves if you had 7 disc, if you're curious. I wrote this out. If you have 64 disc into the 64th power minus 1 winds up being, let's see here, hundreds, thousands, millions, billions, trillions. I think this is quintillions. So it's whatever past quintillions is. If I'm doing my math right, you take that, divide that by 60. That's, assuming 1 move a second. So divide it by 60. That's how many minutes you have. Divide that by 60. That's how many hours you have. Divide that by 24. That's how many days you have. It works out to approximately 585 billion years to solve that problem. Approximately. So, how worried should you be? Probably
well, that's also assuming they make the right move every single time.
Yes, that is also making that assumption.
And then they never have to go back and like undo something.
Or have to teach the person who is going to do it after them, because let's face it, I don't know anyone who's living that long to do it on their own. We're talking you're going to have multiple generations of people doing it, and at some point someone might decide, you know what, this is boring, I ain't going to do it. So you also get into some interesting questions like, what happens if I added a 4th peg? How much faster would it be if I added a 4th peg?
Yeah,
that's a really good question to ask. Or if I had to
pick up the whole stack and move the whole stack.
No. The rule is you can only move 1 disc at a time. That's in the rules. But if I can move if I had a 4th or 5th peg to it, now when I'm moving stuff back and forth, I have more room to spread out, so I don't have to go back and forth so much, duplicating my work. I can just move it right along. So if I had 3 elements, I move 1 to B, 2 to C, 3 to D, 2 goes to D, 1 goes to D, and I'm done. And so I'm done in 5 moves instead of 15 or whatever it is. So does that matter? That's an interesting question that one could possibly ask. The good news is this is actually used a lot of times to teach recursion because of the same type problem being done over and over and over again. So if we look at the solution for it, this is the solution in C++. It says if A is equal to 1, okay? On the last disk, it's really easy to do. Else, we do our tower A minus 1 from to auxiliary, and we have to kind of figure out, okay, where do we move to and where do we go? And this is the whole process. It changes. Notice that when we initially push it in, we do A, B, C. And it's listed up here as from auxiliary and to. Here we do A minus 1 from to auxiliary, but here it's auxiliary from to. So how we wind up moving things back and forth like this as A gets adjusted throughout the list. Each time it gets called, A minus 1 is processed, so we're always subtracting 1 from whatever our call is. Which gets kind of complicated because if I start off with 5, then my next one's 4. When I get called another time, then it's 3, and I get called another time, it's 2, and on that list goes. Because this from to an auxiliary is always being changed up, the order of the pegs that they go in to ensure that they don't overlap in the incorrect sizes is held in check. And so it's a real simple process, but there's 2 recursion calls, moving things and moving them back essentially so they get all lined up. And we have, of course, the large number of recursion calls. The other thing we have to be careful of, some languages, and we saw this, I know Kate saw this in data structures when she had that with me last semester, is like Python, you could only have so many data calls before it says, nope, we're done. And you get a recursion limit. The recursion limit in Python we found was about 960, 990 calls approximately. That's just because of its internal call stack. Other languages have other reasons why they might have that issue. I used to run into recursion problems with Java when I would do fractals. I was doing some fractal math work for a little while, doing artificial landscapes, and I was constantly running into Java problems with it because of its not its call stack space, but the local memory space in the heap would start to run out of space, and so you either had to do some special parameters when you compiled it, so you had more memory space allowed, or you had to have a bigger machine, or it would fall apart. And that's always a potential problem that you run into. This is a hard function to convert to a loop, because while a lot of recursion can be changed into a loop, this makes 2 recursive calls, which makes that converting to a loop basically impossible as far as I know. I've yet to see it done. But this entire piece, that's the whole Tower of Hanoi problem in C++. In fact, if I take this, let's see if I can copy this in. There we go. Okay. So I have my tower function. I have my main function. I go and I run this. Okay. Tower of Hanoi, how many disks? Let's say 3. Disk 1 from A to C, disk 2 to A to B, disk 1 to C to B. Okay. Pretty simple. And it almost shows up right away. If I run this again by, say, 8, it's pretty quick, but notice how many more steps there is, right? Each time I go and I run this, now you can see 12. If I move this out of the way, oh, it just finished. You can see how many more steps it took. You know, just under the nuts category, right? This is the fun one. You can see how long it's taking. Over here is going to tell you your diagnostic time in C#, Visual Studio. It tells us how much memory the process is taking. So notice it's not changing memory usage too much. That's holding pretty steady. And this is the total percentage of all my CPUs. So each core in your CPU usage shows up as a different processor, essentially, as far as programming goes. So while that's staying kind of low, it's actually like pegging out almost fully one whole core. So I have like 8 cores, I think. So you're seeing, you know, we went to like, was it 16 I said that we did? And just poof. Now it's like, wait a second. When we had like 12, it took like 5 seconds. What's with this? And that's because of that big O notation, why it's so difficult. If you notice this drop, we're probably in that second part of that recursion right now, which is why our memory dropped some. Which means we've hit the halfway mark. But we're at 1 minute 19 seconds. Okay. So it finally exited. Ta-da. And we have our time here. Or we don't have a time, but we have the exit of what our move was, our last set of moves. The good and bad news about this from a programming perspective is we're a lot faster than the monks. Well, maybe that's bad. You know, we don't want the hasten the end of the world. But we are much faster. Now, every time we have a cout function or any type of input-output, no matter what your language is. So if you did console.writeLine in C#, or if you did console.log in JavaScript, or any of those things, your cout, your input-output is almost always going to be your slowest process to execute in a program. So whether you're going to say, hey, I want to write this to a file or I want to write this to the screen, that's going to slow your application way, way down. If you took this out, would it be much faster? Yes. Just to give you an idea, of course, we don't get to see what it's moving, but if I comment out my cout statements, the last one took like 1 minute 20 or something like that. I said 18. Saw how much faster I was? Do I need to do that again so you can see it? Okay, so you get an idea of how slow your input output is, right? Your I/O is. What's fun is I can come in here and say, oh, let's do 25, and 25 is a lot, and you saw how quick that was. 32 is taking a little bit to run, but remember how slow the I/O was. Imagine if it was taking this much time. You're going to be looking at your I/O adding, 20 or 30 times this amount of time easily, and we're already at 25 seconds. What's also interesting is if you look, my CPU is much more consistently being used because it's just doing all those function calls. It is not dealing with, I got to write something to the screen, which doesn't take processing power. I got to do something. Write something to the screen, which doesn't take much processing power. I got to do something. Write something. And, that's why you saw that up and down. Got rid of the I/O, and now it's a much, much more consistent thing. Notice also we're looking at coming up on 60 seconds. The other example was about 60 times. Notice here's our little drop, so we're probably at that halfway point where we're calling that secondary recursion call, because remember every function gets called twice. So when we look at this, it's going to take right around 2 minutes, which if we had those I/O screens would probably take close to 2 hours. Just to kind of give you some perspective on that process. So that's an interesting thing. One of the things I want to do is, because this is a C++ application, and we should be coming up. So we should be coming up on when it ends, and we did. Is I would like for you to take this application, and one of the things that we often have to do is, and I've had to do, is rewrite things. So this used to work in Visual Basic, but we're not supporting Visual Basic anymore, so we need to rewrite this for C#, or this was something that was written in Java. Now we need to convert it to this other language. So this is a pretty simple application. All the code is there. It runs. You saw me copy and paste it into C++. But there are some conversion things we have to know about for dealing with converting it. And so for your next assignment, you'll be taking this application that's 100% works, easy to go, and saying, I need to convert this into C#. Now, because C and C# are so simple, and so, I'm sorry, not simple, similar, gotta use the right word, they both start with sim, but because they're both similar, that's going to be a pretty easy conversion, in all honesty. You should be able to go, oh, blank, and get it working for you. But there is going to be some things that you're going to have to convert and whatnot. But it should be hopefully a lot simpler than our last assignment, which was had some hidden complexities to it. But it should give you a little bit of experience in converting language and logic from one to the other. Okay? Any questions on what the next assignment is going to be? It's not written up yet. It's not on Moodle. I will be putting it up there later today. But just something for you to think about as far as that goes. Okay? Any questions on that? No. All right. If not, then I'm going to say you've got we got the rest of our time. You can go ahead and start working on that. That will also be what we're going to do on Thursday. So that way you'll have one whole class to kind of work on that. I'll show up and we can do our meeting, answer any questions you guys run into about that. The other thing I was going to point out, if I come back here. Okay. We will probably be doing a quiz next week. So the assignment will probably be due like on Tuesday. There'll be a quiz. It'll be kind of open-ended when you guys want to take it just sometime next week. You can go through that as you kind of feel necessary. And then we will start working on JSON and working on XML data for the following weeks, which is what we talked about changing that up to. Okay? All right. Tyson, if you want, you can stick around. We're got 8 minutes left of this meeting before it kicks us out, and we can look at your problem and we can see if we can get that solved. If you want. Otherwise, we can schedule another time. Kate, Denise, if there's anything else, you guys can stick around, or if you guys are done, just want to go start working on your assignment or getting a lunch, whatever, you guys are more than welcome to do that too.
We want to know more about that WordPress project that you were talking about the second.
Okay, sure. So let's talk about that real quick. There's a group. I have to get their information again. I've got it buried in my email now. Tim, who Denise, you know Tim Carter. He was on my search committee. He was the head of my search committee. Okay.
Yeah.
He works with some local groups and small businesses and stuff like that, and then they provide through the business school consulting and advice and stuff like that. Well, they had some questions on doing a website, and so they wanted to. He wanted to see if we had some students that would be able to help that. They are looking at doing a WordPress site, and so it's a content management system. It makes it real easy to handle as far as that goes. So it'd be mostly putting in contact information, possibly setting up and configuring a few widgets and plugins, and building out, picking the right theme to use and modifying the theme if necessary. I can help with all those. I've done all those. I cannot see a reason for them to need any custom, truly custom programming from what I've seen in the project. But if, regardless, we would need to talk to Tim and get final requirements and stuff like that. And I'd be more than happy to contact him to make that, connection with you guys so you guys can talk and Kate, you can talk. I don't know if you know who he is or not, Dr. Tim Carter. But we'd be more than able and willing to do something like that if necessary.
Yeah, because we were talking about it and we were not sure how much work it's gonna be because the other project is gonna be a little bit shorter than it is now.
Mm-hmm. And to be honest, I don't fully know. I just know the high, like 10,000 foot level. What the project is on. Like I said, I don't think it's going to be an overwhelming amount of work, but I think it's something that's always good to help build a portfolio. So when you're talking either to an employer or a grad school, I know both of you guys are interested in grad school. Something to say, hey, this is something else we've done and what we're looking at. So those type things, especially since it's helping with training of service animals, it's kind of a warm, fuzzy feeling type of thing. You know, if you were doing something like, oh, this is our local widget maker, people are like, yeah, that's nice. Well, this group trained service animals for people with disabilities. Aww, you get warm fuzzy karma points for it regardless. So that's why I thought I'd bring it up and suggest it as far as that goes. Okay, I'll let you guys kind of talk, and if you guys just give me kind of a decision tomorrow morning, I'd appreciate it. You can just email me if you want.
Okay.
And figure out, and then like I said, I'll be happy to help train you and teach you anything that you need to know going forward as far as that goes.
Sounds good. Thank you.
All right, you're welcome. I'm going to stop sharing. And Tyson, that way you can go in and share.